covered. I know you've already covered, some of this work, especially around things like depth-wise convolutions. What I wanted to do in this lecture was just step back a bit and talk about the history of trying to build efficient models. What the motivation is, and what the kind of progress has been over the last few years. So the first question is really, why do we care about making ML applications efficient? Why is this such a concern? Because it isn't obvious from the research side why there wasn't traditionally much motivation for efficiency, because people cared about accuracy. Like, just getting this stuff working was super hard. Everybody for the first few years was looking at model accuracy on ImageNet initially, and didn't really focus on how big or how much time the models took to execute. But it's actually, even in those days, there was an informal focus on model efficiency, because people had to train these models. And the usual rule of thumb was that once a model took more than about a week to train, it became really hard to work with it, because the iteration cycles just became way too long to sort of make all of the tweaks you need to actually get a model towards accuracy. So even in those early days, there was a kind of an unspoken focus on efficiency, just so that people would even be able to train these things. But as ML applications have become more and more mainstream and used more widely, it's become this massive concern. And even in the cloud, the amount of energy that's used, especially in data centers, translates in a very straightforward way to money that you're spending. So it's important for applications to be feasible that you actually keep your compute memory and storage under control. And then, as you'll have kind of probably discovered at the edge, you have not only very tight resource constraints, but they're resource constraints that are very hard to expand beyond, especially for memory and storage, because you just have hard limits. You have no kind of swap space, or you can't just pay more money to get kind of a larger cloud drive. If your stuff won't fit, then you just can't ship. So models are almost always the prime factor for how much space and how much compute you use. So they are the first place to look to actually see if we can reduce our resource usage. And you might be thinking, oh, especially for things like latency for or throughput, or just overall kind of time performance. Oh, maybe I'll jump in and start trying to modify the code so that it runs more efficiently. And that's definitely, something worth doing, but only after you've made sure that you're doing as little work as you can at a high level. It's probably something you'll have run across in, the computer science side, is you really have to think about figuring out if you're running the right algorithm at a high level before you start doing low-level optimizations, because you can never optimize something better than not doing it at all. So if you can figure out how to do less work at the high level, you're going to be in a much better position. So, the idea in the computer science side is usually something like figuring out the right sorting algorithm. But the equivalent in ML is picking the right model architecture. So picking the right operation types, picking how they're actually chained together, and also picking the right parameters for those layers that you're putting in your model. And that is really going to be the way that you're going to get the most efficiency. Now, I'm going to recommend that you avoid designing your own models, if at all possible, because there still isn't a good kind of roadmap for how to do this stuff. Just designing model architectures in general is still more art than science. There's just a lot of experience and experimentation needed before you can actually figure out how to build something that is a good trade-off between accuracy and efficiency. So your first step should really be, hey, I need to do something that's more efficient for this problem. Let me go out there and see what other people have already built. So looking at things like Hugging Face, looking at architectures like MobileNet or YOLO or some of the other ones I'm talking about, is gonna be a much better idea than kind of trying to start something from scratch. But even as you're choosing those models, it's actually really useful to at least know some of the design trade-offs. So I'm gonna sort of dive in, even though I don't recommend you use this knowledge, to start trying to build your own networks unless you really enjoy pain. So jumping back in time, the model that really started this whole deep learning explosion was AlexNet. And this was the model that I was working with on my startup back in sort of 2012, 2013, where we were doing image classification, and it was big. It was I want to say over 150 megabytes, I think, with float weight parameters. And just one of the fully connected layers at the end was almost 40,000 parameters. And it had these big kernels like 11 by 11 and 9 by 9, which by modern day standards are extremely large, and they involve a lot of compute. So AlexNet's big feature was that it worked, which was super new. And was kind of a revelation to everybody, and got a lot of us started in this field. But there was not much focus on efficiency, though again, like coming back to this idea that there was still an efficiency sort of requirement. The real secret of AlexNet was that Alex actually wrote a really good CUDA implementation to actually train this model. So it was actually possible to train this in about a week or so. So even though by modern day standards, it's a lot less efficient than it could be, the reason it worked at all was because it was possible to train it in a reasonable amount of time. So this got widely adopted because it worked and previous attempts just did not work. Then, people started to really take this AlexNet sort of idea that was working, but then figure out how to both increase the accuracy, which was still, the thing that people really cared about. Everyone was looking at like the top 1 and the top 5 accuracy on ImageNet and sort of competing to come up with, models that did a better job, like Inception and ResNet and, some of these others. But especially as this started to become less research and more engineering, efficiency started to get a bit of a look in. It started to get a bit of a mention as people were publishing these models. Like the size of the model and the amount of compute it required, they actually started getting listed in the papers, even though getting a model that was more accurate than the current state of the art was still the thing that came first. And it's worth at this point stepping back a bit. And I've been talking about efficiency, but what does that actually mean? So it can mean a whole bunch of different things. Latency is the obvious one. Like, how long does it take to do one inference? Throughput is a slightly different one, where if you're doing batches, it may take the same time to do 100 images that it takes to do one image. So if you can batch them together, you may actually get a much higher throughput, even if you don't increase latency or reduce latency. File size can be important, especially for embedded systems, as you found, and how much memory is being used for scratch and activation buffers. And one thing that kind of comes back to, relates to latency and throughput and some of these other things is energy usage. And what's most interesting about models is that they tend to be, it tends to be possible to slightly reduce accuracy to increase, the performance on some of these other measures. So it's a really nice property of machine learning models that you usually have some dials and sliders that you can move to be able to decide what the best trade-offs are for your system that you're trying to deploy. And the other thing that's interesting is we often talk about accuracy like it's this single objective measure. But one thing I pretty quickly discovered when doing kind of real world applications is the evaluation metrics are really only approximations, hopefully with some correlation, to the quality that you want in your application. And I still like, what somebody told me once was that the real the only loss function they really care about is the App Store rating of their product. And that was useful for me, because then it kind of helps you think back, hey, we're not just going for this abstract number that we're trying to get up, we're actually trying to improve the user experience. And a good example of this was actually WordLens, which was a startup that was acquired around the same time as mine was in 2014. And they had this really neat app where you would point your phone at a foreign language sign or menu, and in the camera, it would actually show you the translation of that, that word or phrase. And Google Translate actually already had a similar feature. But what they would do is you would actually point your phone, you would click to take a picture, that picture would be sent off up to the cloud, and then you would get the translation back on your phone. That process took a few seconds. And there was some, grumbling, let's say, by some of the people who were existing Google engineers, because the accuracy of WordLens's solution, which was running on device, if you ran the evaluation metrics, it was significantly lower than the accuracy of this server-based approach. But what we found was that people's users' experience of the model, they experienced the WordLens model as more accurate because they were getting real-time feedback. They were able to kind of wiggle the phone so that the letters kind of locked into place, because it was running at several frames per second. So what I found really interesting about that was, even though the evaluation metrics of the on-device model were lower at just looking at the raw training values, when you actually looked at it as part of the application, the model on device worked better because of the interactivity and the low latency that was actually running. So that's my go-to example of why you should always take evaluation metrics from training with a bit of a pinch of salt. You have to think about how they're actually going to manifest themselves as part of an application, and how latency and interactivity can actually help something become better quality in terms of an application. So model efficiency isn't just about kind of saving resources and money. It really can help improve the experience for the users as well. So having said all that, I'm not going to spend too much time on this stuff, because I think you will have covered, a lot of these, previously in the class. But I do want to kind of point out this evolution that's kind of taken place over the last few years as we figured out how to make models more efficient. And Inception v1, or GoogleNet, I guess, I never know quite how to pronounce that. Their big innovation was, if we go back to AlexNet, you'll see that we have these 9x9 and 11x11 convolutions, and they are very big. They require a lot of compute to actually implement. So what Inception did was actually break those down into, instead of doing one big set of 9x9 or 11x11 convolutions, they actually said, hey, let's actually take these sort of convolutions and sort of break them down so that some of them are just done by 1x1s. We have some 3x3s. We do some, max pooling, and then actually feed them through a 1x1 convolution to kind of, sort of shrink down some of the filters, like some of the numbers of channels at the start as well. And these all have the effect of sort of taking, if you imagine this like 3D cube of the 9x9 or 11x11 convolutions, it's actually sort of breaking them down into much, several different cubes that are much smaller in each dimension. And so can get a lot of the similar coverage to the 9x9 or 11x11s, but with a lot less compute. And you'll see that this is a kind of a recurrent theme for the changes that we went through to try and improve efficiency. So Inception v2 did something similar, but instead of just breaking these big convolutions into sort of smaller cubes that were kind of fed through each other, they actually took some of them and broke them into sort of 1x(n) and n/1 versions. And this worked because a lot of the patterns in the convolutions were could be well represented by basically taking, instead of like a square convolution, you take a horizontal and a vertical and just kind of convolve them together. And again, that's like a lot less compute. And then MobileNet was really interesting because not only because of the kind of innovations it introduced with some of the modules and some of the ways it did convolutions, and I'll quickly cover depthwise convolutions, but because it explicitly offered different versions that had different trade-offs for the amount of compute and the amount of memory required. So it effectively offered you a menu of saying, hey, I actually need to fit in this particular size, so I am able to kind of make these accuracy trade-offs to fit in with this particular size, and gave you this set of different models where you could effectively kind of move a slider to control how much compute and how much memory you actually needed. And that was really a fantastic breakthrough, because it meant that the model designers themselves did a lot of the work for you. So you didn't just have to kind of hope that somebody had the exact sized model that you were looking for. The other thing that they did really well was this idea of depthwise convolutions. And kind of like I said, if you think about this geometrically, what we did was AlexNet had these big 9x9 or 11x11 convolutions that used the full set of channels as their inputs. We've kind of kept breaking the these big monolithic convolutions into smaller components, which are good approximations of them. And then MobileNet v1 actually broke them into channel-wise operations. So you've covered this before. I won't go into too much depth, but it's kind of this extra step, this another step towards kind of breaking these big compute-hungry operations down into things that operate on much smaller subsets. Reducing the computation as we go. And there's a really nice amount of parameter saving that you get through that, as well as computation saving. Now, the last thing I want to talk about is network architecture search, because this often sounds like kind of a panacea, like a universal solution for all of our problems. It's like, well, why don't we just let the computer design the model for us? Well, the first NASNet was a really big breakthrough in a lot of ways, but the mobile version, even though it looked like the model that it produced, even though it looked like it had fewer ops, fewer arithmetic ops than something like MobileNet, it turned out it actually ran a lot slower because just the raw number of arithmetic ops was not a good approximation of how fast it was going to run. So what we did with future NASNet releases was we actually worked with Quark and the team to run models on real devices to get a better estimate of their speed. So we were able to actually, instead of just using the number of ops, we were able to work with them to help them pick models that we're going to run well in practice. And it also, it turns out that network architecture search usually only covers a fairly small part of the search space. So you also have to be pretty careful about how you pick the parameters and kind of the starting point that you use for your network architecture search in order to get good results. So it turned into much more of a collaboration between the teams who were doing manual model optimization and the teams that were doing much more kind of automated approaches. And that was really nice to see. And just very quickly, I wanted to talk about YOLO, which is, a fantastic family of models that you might well run across, and why one-shot is so important. And the example that I like to use is this really mysterious bug that we were hitting where the photo upload servers would sometimes crash, and we couldn't figure out why. And it turned out that what we were doing was actually finding all of the faces in an image and then running a model inference on each face. So this is kind of like the two-shot approach. And what happened was that if you had images like this, there would be so many faces that running all of those model inferences would just time out the server, and the process would crash. So if you're able to actually do one shot with something like YOLO, it means that the model remains kind of linear time and doesn't depend on the input. So you can avoid all sorts of kind of gnarly issues like that. So I know I only have a couple of minutes left. So that's the material I wanted to cover. Like I said, feel free to reach out with any questions. I'm always happy to chat. And I don't know, Raoul, if there's 1 minute for questions or how you want to do this.
Yeah, there's time for questions. Any questions? Yeah, there's a question here.
Yeah, so when you use your models, like the ones you were talking about, like ImageNet, the ResNet, AlexNet, etc., like for those things, when you choose your model, do you care about training time? Since like training, like when you deploy it, like you aren't training it when you deploy it, you only like train it when you're like doing the research part of it. So like for like users, doesn't matter which model you use besides accuracy.
So I don't tend to care about training time, but mostly because the size of the models that I'm using for deployment is usually so small that the training time is at most measured in hours. One thing I didn't really cover actually was the way to kind of approach this from a model training point of view when you're trying to target efficient models. I would always just use an off-the-shelf kind of cloud-focused model to start with, just to see if you can actually get the accuracy you want on your data set. So don't worry about creating an efficient model right from the start. Just make sure that you get your data set right first and use as big a model as you need. And only once you've actually got the good enough results on as big a model as you want on the cloud side, only then start thinking about using an efficient model. So that's kind of a two-part answer, I guess, is, I don't really care about, as long as you can train something in a few days, you're usually in a pretty good position. And only then, once you're sure that your data set has enough signal in it to be able to train at least one model, only then start looking at the efficiency side.
Cool. Thanks so much, Pete. I have one last question. So as you've been hiring over the years, what's one interview question, you don't have to give the answer, to the class that you would want to part with, and so they can think about it, and then we can get back to you when we see you again later in December.
Yeah, well, one of my favorite interview questions is, just tell me about a time when you ran into a bug in a library or a framework, because I think anybody who's actually had some real world experience doing programming will have run into something like that. Or maybe it's even a case where it turned out it wasn't a bug in the framework or library or compiler, but you kind of thought it was. And just tell me about the process that you went through to figure out what was going on, because it's that problem solving and that ability, honestly, to just deal with the frustration that I think is the one of the biggest qualities you need to be successful in kind of actually building things like this.
Great. So you guys have something to think about. And so let's give Pete a big hand. I think, yeah, thank you so much.
No, thanks, everyone.
I think no one else could give us this actual verbal history of what would happen behind the scenes to come to this TinyML kind of course. And I'll follow up with you, Pete. Thank you so much.
Okay, thanks, everyone.
Bye.